Swayam Prabha. Digital India. Educated India.
Welcome to the second lesson of the second module on the course of strength of materials, in which we are going to discuss today on the analysis of strain, part 2. And in the last lesson we have introduced the strain after discussing the different aspects of stresses in module 1. Now in this particular lesson it is expected that once it is completed, one should be able to understand the concept of axial and the normal strain in a stressed body of variable cross section. In the last lesson we had discussed about the strain, the axial strain, the normal strain in a bar which is of uniform cross section. In this particular lesson we are going to discuss that if a bar is of variable cross section, then what will be the strain in that particular body. To understand the concept of shearing strain, also one should be able to understand the concept of shear modulus and Poisson's ratio. Hence the scope of this particular lesson includes the recapitulation of the previous lesson. In the lesson what we have discussed in the first one, we will look into it through the question answers. Then the evaluation of axial strain in a body of variable cross section, evaluation of shear strain and shear modulus, and subsequently the evaluation of Poisson's ratio. We will see the meaning of Poisson's ratio and then evaluation of Poisson's ratio in a body which is subjected to loading and undergoing stresses. Well, before we proceed, let us look into the questions which I had posed last time. Now, the first question which was posed was what is meant by elastic limit. Now, let me explain this with reference to the figure. Now, if you remember, last time I had demonstrated that the stress strain relationship is of this particular form, where this axis represents strain and the y axis represents stress. Now, I had said that if we keep on applying load on a bar in an axial manner, if we apply a tensile pull to a bar gradually, the bar will undergo deformation, and thereby we had seen that for a bar which is subjected to axial pull, how to compute the strain corresponding to that for each increment of the load. Now, if we compute the strain for a particular load and compute the stress corresponding to that load, we can get a plot of stress versus strain. Now, up to a particular limit, if we keep on applying the load, on removal of the load, the bar is expected to come back to its original position. But beyond a point, if we keep on applying the load, the state of stress and the strain in the bar will be such that it will not come back to its original position after the removal of the load. Now, the limiting point up to which on removal of the load the material comes back to its original position, we call that as elastic limit, and this is what is indicated over here. And up to that limit, we expect that the stress is proportional to the strain, which is popularly known as the Hooke's law. Second question was what is the difference between nominal stress and true stress. In fact, while discussing this stress strain curve, I had explained that when we compute the stress at any point in the stress strain curve, the stress at any point is given by the applied load divided by the cross sectional area. Now, when we take the original cross sectional area, the stress thereby which we get P divided by cross sectional area, we call that stress as nominal stress. Whereas, as we are applying the load in the specimen and beyond elastic limit, the bar is expected to have a reduced cross sectional area. If we calculate the stress based on this reduced area, we will get P divided by the actual cross sectional area, which is little higher than the stress is higher than the nominal stress, and that stress P divided by actual cross sectional area, we call that as true stress. So, P divided by the original cross sectional area is the nominal stress, and P divided by the actual cross sectional area will give us the true stress. Now, before we third question posed was how will you evaluate strain in a bar with gradually varying cross section. Now, today's lesson is based on this, but before we go on this particular question, let us look into that how do we perform a test on a tensile specimen in a tensile pulling equipment. This experiment is primarily the tensile testing of a HYSD bar. HYSD stands for the high yield strength deformed bars, commonly termed as torch steel. We are interested to evaluate primarily three aspects of it: the yield strength of the bar, the ultimate stress, and the percentage elongation that the member undergoes. The bar will be tested under constant axial pull, and it will be the load will be applied till the member fails. The whole length of the bar has been divided into a number of segments, and each segment measures 40 millimeter. After the specimen is tested, after failure, we will remeasure the lengths and we will see how much extension this individual segments has undergone, which will give us the measure of the elongation that the material has undergone. The objective of this particular test is to evaluate again the yield stress of the material, the ultimate stress at which it fails, and the elongation it undergoes, which gives us the measure of the ductility of the specimen. This is the control panel from which the load will be applied to this particular specimen at a constant rate till the member fails, and the type of load that is being applied onto this particular specimen is a tensile pull. Now, we will look into how the load is being applied on the specimen till its failure. After the bar has been tested, if we look into the failure of the bar, we will see that one side has formed a shape of a cone and other side is that of a cup, and this kind of failure is generally called as cup and cone failure. Now, if we look into the whole length of the bar, you will find that at the central part, it has undergone extension, and because of plastic deformation, the length has been extended. If you remember, in the beginning we had divided the whole length of the bar at a segment of 40 millimeter. Now, if we measure the extended part of that particular segment, now after it is elongated, we find that this particular length, which was originally 40 millimeter, is now 54 millimeter. This indicates that this particular bar has been extended by 14 millimeter. This gives us a measure of percentage elongation and thereby the ductility of the material. Well, just now we have seen the experiment which has been performed on a bar applying a tensile pull, and then it has snapped at a point, and the type of failure you have observed, which we call as a cup and cone failure. Now, if you remember, in the last lesson we were discussing that if we apply a tensile pull in a bar, the bar is expected to undergo deformation gradually, and at certain point of time it undergoes failure, and that is what is represented in this stress strain curve, that if we apply load gradually up to elastic limit, if we release the member comes back to its original position, but if we keep on applying the load, it undergoes to the maximum stress and then fails at a lower value. Now, this part we called as a failure stress, and this part the maximum stress we call as ultimate stress. Also, if you have noted, we have measured, we had in the last lesson we said that in a particular area in the bar, we generally reduce the cross sectional area from the entire original area. The purpose of that is to concentrate the failure in that particular zone, so that we can observe how the failure is occurring in that particular member. Now, in this particular experiment which we have seen just now, there we have not reduced the cross sectional area as such, we have applied a pull to the bar, but the whole bar was marked with segments of 40 millimeter. Now, after the application of the tensile pull, the segmental lengths which was originally 40 millimeter was measured again, and the segment in which the failure had occurred, we measured the extension which we found to be around 14 millimeter. Now, this gives us a measure of how much elongation the member can undergo before really it fails. At a later lesson, we will look into the implication of this elongation and how that is taken into account in engineering application. Well, let us look into now the question which I had posed, the third question, that what happens if we apply now axial pull in a bar, which the cross section of which is no longer uniform, but it varies gradually, such as that of this particular one, as it is indicated in this particular figure. Now, in the previous lesson we said that if we apply a load P, axial pull P in a bar, it undergoes deformation, and from its original length L, it becomes L plus delta, and this extension delta we had seen how to compute. Now, if instead of having such uniform cross section, if the cross section of the bar is varying, say we have an area here which is A1 and the cross sectional area here is A2, and this bar is having or subjected to an axial pull P. We assume that this area is varying linearly between A1 and A2 over the length L. Now, this cross sectional area or this bar can be of cylindrical type, thereby we can compute from the diameter could be varying, or we can have a rectangular cross section in which the thickness is uniform, and thereby because of the change in the width the cross sectional area is varying. Now, at any cross section which is at a distance of x from the left end, the cross sectional area of this bar is going to be equals to, this is A1 plus, if we take a line down, this is also A1. So, this particular length is A2 minus A1 by 2. So, this is A2 minus A1 divided by 2 into, at this point it will be x over L, and since we have this unit plus this unit which will give me the total area over here. So, times 2. So, this is equals to A1 plus A2 minus A1 times x upon L. So, this is the cross sectional area over this particular segment. Now, if we like to find out the elongation of this particular bar, which is delta. So, as we have seen in the last lesson, delta is equals to PL over AE. Now, since here the cross section is varying at every segment, let us say we take a small segment which is dx. So, this is equals to integral of P over AE, A is also function of x now, dx, which is varying from 0 to L. Now, we substitute the value of A here, which is a function of x, and integrate it over the length, which will give me the deformation delta. Also, sometimes we can compute the extension by considering the whole of the bar into a number of segments. If we divide the whole of the bar into a number of segments, and if we consider one of such segments, now on an average, say this is area A1, this is area A1 dashed. On an average here, we can say the area is average of this area plus this area by 2, and which is constant over this particular segment. Here we are adding something, here we are subtracting something. So, on an average this satisfies for the whole segment. So, for this if we compute delta for this particular segment, likewise we can compute delta for each of these segments, and if we sum them up we get the total delta for the whole of the bar. But since we are dividing the whole bar into a number of segments, it is expected that, and we are approximating that the area is average of the two ends. So, it is expected that we may get a little error into it. However, we can compute, instead of going for a rigorous calculation, we can sometimes compute the elongation in the bar in this manner. However, for a precise analysis, the deformation delta should be computed using this expression. Now, let us look into that if a bar which is fixed at one end, so at this end the bar is fixed and is being pulled by an axial pull P. This is of length L. Now, as we have seen earlier that when the bar is being pulled, it is undergoing extension. This is the extension delta, and we have seen how to compute this extension as a function of this axial pull P in terms of the cross sectional parameter A and the length L. Now, when this is being pulled, the bar undergoes deformation in other directions as well. In fact, when it is being pulled or elongated in axial direction, it undergoes contraction in other directions. and this is what is a interesting one, that if it is stretched by an axial force, then there is a contraction in the transverse dimensions as well. Now, Poisson demonstrated that the ratio of this transverse strain to the axial strain is constant for stresses within proportional limit. So, within elastic limit, within proportional limit where stress is proportional to the strain, the transverse strain which we get because of this axial pull, the ratio of this transverse strain to the axial strain or the longitudinal strain is constant, and this particular constant is called as Poisson's ratio. So, as we have seen that when the body is being pulled, when this particular bar is being pulled by axial force P, it undergoes deformation in the axial direction. If we call this as x direction, then it undergoes deformation in the x direction, and thereby the strain which we designate by epsilon, we call in the x direction strain as epsilon x, which we can compute in terms of P L cross sectional area and modulus of elasticity of the member. Also, it undergoes deformation from its original, if this dotted line is the deformed configuration. So, from its original depth, the depth also reduces, thereby it undergoes some deformation over here delta dash. So, the deformations, as Poisson had observed, that this deformation, the transverse strain, the transverse strain to the axial strain, it remains constant for stresses up to the proportional limit, and this is what we designate as Poisson's ratio, commonly designated as mu. Sometimes it is designated as the Greek symbol nu as well. So, mu is called as Poisson's ratio. Now, for uniaxial loading, when the bar is subjected to uniaxial pull in the x direction, the Poisson's ratio from the definitions as defined just now is equals to the lateral strain to the longitudinal strain. Now, please note here that we have introduced a negative sign in this particular expression. This indicates that when the body is being pulled in the axial x direction, in the other direction it is undergoing contraction, and that is why this negative symbol has come over here. So, the negative sign indicates that an elongation in the axial direction causes contraction in the transverse directions, and the transverse strain is uniform throughout the cross section and is the same in any direction in the plane of cross section. And this is important points to be noted, that the transverse strain which could be in the y and the z direction is uniform throughout the cross section and is the same in any direction in the plane of cross section. So, this leads to the fact that for uniaxial loading, that means a bar when it is loaded in the x direction with an axial pull P, the contraction or the deformation in the y and z direction, if we call this as x direction, this as y direction and this as z direction. So, the strain in the y direction, which is deformation to its original length in the y direction, epsilon y, is the same as that of epsilon z, as we said that in all direction it is the same, is equals to the minus mu times epsilon x, where mu is the Poisson's ratio. So, lateral strain to the longitudinal strain is equals to the Poisson's ratio. So, thereby the lateral strain in the y or in the z direction, they are equals to the Poisson's ratio times the axial strain. Now, in the previous lesson we have seen that when we relate the stress to the strain in the up to the proportional limit or up to the elastic limit, the stress sigma is proportional to the strain, or sigma x is equals to E epsilon x. Thereby, the strain epsilon is equals to sigma x by E. Hence, the strain in the transverse direction epsilon y or epsilon z in terms of the axial strain is equals to minus mu sigma x by y. In place of epsilon x, we substitute sigma x by E, which gives us mu sigma x by E. Now, this particular concept can be extended to a planar body. If I have if we take a planar body in which we have the stresses, normal stresses sigma x and sigma y, and if we say that its original dimension is say delta x and delta y. Now, when they are being pulled, they will undergo extension. Now, when it is being pulled in the axial direction sigma x direction, it will undergo elongation in the x direction, it will undergo contraction in the y direction. When it is being pulled in the y direction, it will undergo elongation in the y direction, and there will be contraction in the x direction. Now, if we take independently that when it is undergoing elongation in the x direction, which is epsilon x, which is equals to sigma x by E. Correspondingly, the strain in the y direction epsilon y will be equals to minus mu sigma x by E as per the definition of the Poisson's ratio just now, which you have observed. So, this is the case when sigma y is not there, the planar element is being pulled by the axial pull in the x direction. When the plate element is being pulled in the y direction and having no load in the x direction, it will undergo elongation in the y direction, and thereby there will be contraction in the x direction because as per the Poisson's definition. So, when it is being pulled by sigma y, we have the strain epsilon y is equals to sigma y by E, and correspondingly epsilon x is equals to minus mu times sigma y by E. Now, if we consider the case when this plate element is being subjected to sigma x and sigma y simultaneously, when it is under the action of pull in the x as well as in the y direction, then we can superpose the effect of these individual results, because we are within the proportional limit or within the elastic limit, and as a result we can superpose the results of the two, and thereby the epsilon x finally is for simultaneous action of sigma x and sigma y is going to be equals to epsilon x from here as sigma x by E, which is the direct effect, and because of y is minus mu times sigma y by E, and likewise epsilon y is equals to sigma y by E minus mu times sigma x by E. So, these are the strain in the which is for simultaneous action of axial pull both in the x and y direction. Now, having looked into the strains in the axial directions when it is acting only in one direction or acting in the two directions, wherein we have the strains epsilon x, epsilon y. Now, when we discussed in the stresses that we encounter stress which is in the x direction, in the y direction, and also we undergo the body undergoes at a point a stress which we call as a shearing stress, which acts between the two planes. So, if we look into such a case where a particular body is subjected to, let us say this body is fixed at this particular end and it is subjected to a horizontal force P which is acting on this plane. Let us assume that this plane has a surface something like this, maybe this length is L, this width is B. Hence, the force which is acting on this plane will cause a shearing stress which is P divided by L times B. This is the shearing stress. Now, if this particular body is fixed at this particular end and this horizontal planar force will try to cause a deformation in this particular body, and it is expected that in its deformed state it will undergo deformation as shown in this dotted line. Now, by this deformation, the angle which we get here, this we call as the shearing strain and denoted by the Greek symbol gamma. So, gamma is the shearing strain. And this is what is defined here. The shear strain is defined as the change in a right angle of a body. You see that when this particular body which has a right angle over here, after the action of this planar force which is causing deformation in this body undergoes a deformed state, and thereby this right angle undergoes a deformation, and this angular deformation is termed as the shearing strain, and generally it is measured in radians due to the applied shear stress. Now, as we had observed in case of the stress and the strain in an axial pool, that up to the proportional limit or up to the elastic limit, the stress is proportional to the strain. Likewise, here the shear strain also is proportional to the applied shear stress. So, in an elastic body, up to the elastic limit, the shearing strain is proportional to the applied shear stress, or the shear stress, as we have seen earlier, we designate it by tau, and shear strain, as we have seen now, we designate that by gamma. So, tau is proportional to gamma within elastic limit, within the elastic limit. And thereby, if we remove this proportionality constant, we can say tau is equals to G gamma, and this proportionality constant G is commonly known as shear modulus, or many a times we call that as rigidity modulus. So, the G is the shear modulus which is equals to tau divided by gamma. So, the shearing stress by the shearing strain gives us the shear modulus G. And this is an important result which we will look into how, as we go along, to apply this or to evaluate the stress or the strain in a body when they are subjected to different kinds of loading. Well, now we come to the some example problems based on the aspects which we have discussed. In the last class, I had posed you a problem that which is like this, that an aluminum bar which is having a cross sectional area of 160 millimeter square carries the axial load as shown over here. We will have to compute the total change in length of the bar, and the modulus of elasticity E is given as 70 GPa, the gigapascal. Now, if you remember, we had solved one problem which is similar to this, but we had different cross sectional areas for the different segments, in which we had computed the extensions of the different segments, and finally we had added the extensions to get the final elongation in the bar. Now, in this particular case also, since there are variations of the loads at different points, the first thing which should be checked is whether the applied loads keep the body in equilibrium or not. Now, if we look into that 35 kilonewton is acting in the negative x direction, 10 kilonewton is acting in the negative x direction. So, total force that is acting in the negative x direction is 45 kilonewton, and in the positive x direction 15 kilonewton and 30 kilonewton, two forces are acting. So, thereby this body is in equilibrium under the applications of the forces in the bar. Now, last time when we had solved a similar example, if you remember, what we need to do is here also from this point to this point, let us say this point is A, this is B, this is C, this is D. Now, from A to B, just a little below B, the effect of force which is existent is this 35 kilonewton. So, if I take a cut here and make a free body of this, of the part AB, just prior to the application of this 15 kilonewton load, then this is 35 kilonewton. So, to keep this bar in equilibrium, you will have to have a resisting or the reactive load which is 35 kilonewton. Now, this application of the load extend or elongates the bar. So, the extension of this part under the application of 35 kilonewton will be delta is equals to P L by A E, which is equals to P here is 35 kilonewton. So, 35 into 10 to the power 3, so much of Newton. L of this segment is 0.8 meter, which is 800 millimeter, divided by the cross sectional area. Here the cross sectional area of this segment is 160 millimeter square. So, 160 multiplied by E. E for this particular material is 70 GPa, which is 70 into 10 to the power 9 Pascal. This value, if we compute, comes to as 2.5 into 10 to the power minus 6 millimeter. Now, this particular bar, since it is undergoing axial pull, the tensile pull, so this is positive elongation. Now, let us look into the free body at this particular segment. Now, just after the application of this force, if we cut the bar, then we have the forcing system something like this. Here we have 35 kilonewton. At this point, we have 15 kilonewton. Now, 15 kilonewton is acting in the positive x direction, 35 kilonewton is acting in the negative x direction. So, the balance is 20 kilonewton on this side. So, to make this part in equilibrium, we have to have 20 kilonewton acting in this side. So, this will make the body or this particular free body in equilibrium. So, this particular segment, the part of the body immediately after the application of this load to the point prior to the application of this load, this particular segment will have a force system which is something like this. Since 20 is acting in this way, so the resistive 20 will be acting in this, and so for balancing this it has to act in this form. Thereby, this bar will undergo stretching because of this 20 kilonewton load,